Hello, everyone. Welcome to the session on design guidelines. My name is Elfie, and today we have three exciting talks for you. Our first talk is on design patterns and trades-off in responsive visualization for communication. It is a joint work by Hyeok Kim, Dominik and Jessica Hullman. And now I'm going to hand over the stage to Hyeok to present their work.
Hello, I am Hyeok from Northwestern University. On behalf of my colleagues Dominik and Jessica, I will present design patterns and trade-offs in responsive visualization for communication in this talk. Drawing an analogy to responsive web design, responsive visualization refers to presenting a visualization for different types of devices, commonly including large screen devices like desktops and laptops, and small screen devices like smartphones. As more and more people access data visualization on small screen mobile devices, as well as large screen devices, needs for authoring responsive visualizations are increasing. In general, reduced screen space, different aspect ratio, reduced computational power, and simpler purposes for shorter amounts of time are commonly known constraints for designing responsive visualization, particularly for mobile views. In practice, many tools are relying on a small set of simple, easily automatable heuristics, such as truncating or removing long label text with ellipses, and disproportionate or proportional rescaling, etc. Identifying effective responsive transformations, those that preserve important characteristics of a design, is tedious for authors who must cycle through strategies and judge the results of each one. In addition, the design space of responsive visualization itself may be larger than what individual authors are currently aware of, causing them to overlook strategies they are not already aware of. Therefore, an automated approach to design recommendation is necessary, and the first step toward it is a deeper understanding around design patterns and trade-offs in responsive visualization to inform future work about constraints and grammar for such automation systems. To that end, our work contributes 76 design patterns for responsive visualization and forms of trade-offs between maintaining graphical density and preserving intended messages or takeaways. To derive design patterns, we first qualitatively analyzed 378 pairs of large screen and small screen views of responsive visualization cases. We looked at data visualizations from news articles, data reports of international organizations, and blog posts of visualization designers, etc. Our sample is composed of different types of representations, such as bar charts, line graphs, maps, and scatter plots. We also included different types and sizes of data and various formats of visualizations, such as static, small multiples, interactive maps, dynamic queries, and animations. Before introducing our results, I will first describe several example cases. These examples are redrawn and conceptual, but based directly on examples from our sample. In the large screen view of this case, the x-axis encodes years, and the y-axis encodes the predicted GDP growth rate. Each line segment is a predicted change of GDP growth rate for 5 years. The line segments for the predictions made in 2010 and 2016 are highlighted by red color and annotated. Here is the small screen view. The biggest change is the removal of two lines that represents the 5-year prediction of 2010 and 2011. Possibly because of that change, the annotation and emphasis to 2010 prediction are omitted. In addition, the relative width of the chart is also reduced. This example illustrates responsive design transformation can affect different levels of editorial decisions, from what data to include to how to emphasize important data points. Here is another example. In the large screen view, each bar composed of small face images represents the number of the white male cabinet members of the corresponding president of the United States. Each face image is a cabinet member, and viewers can check who the cabinet member is by hovering a mouse cursor on an image. In the small screen view, the most noticeable change is the omission of the face images, because it is no longer necessary to identify each square. The tooltip is also removed. Lastly, the labels and bars appear in a vertically serial order on small screen. However, a similar representation does not always result in the same responsive transformation. This is another visualization from the same news article of the previous example. In the large screen view now, each bar is composed of face images of every cabinet member of a president, where female members are denoted by purple and non-white male members are colored by green. In the small screen view, while the face images are maintained, the axes are transposed. The tooltips are also maintained, but its position is now fixed at the bottom of the screen space, perhaps for more efficient use of the screen space. We speculate the preservation of face images is because of different narrative roles of visualizations in an entire article. The article is about the representation of minority groups in the cabinet members of the United States. This one includes more comprehensive information that the article is about, providing an overall snapshot. In contrast, the authors of this article might have dropped face images from the previous visualization, presumably because it has relatively partial information, which is about just white male cabinet members. Through analyzing in that way, we derived 76 design patterns. These are pictograms of some of our design patterns. We provide design patterns on our online gallery with pictograms and definitions. We describe our design patterns in 2 dimensions, targets and actions. Target refers to what is changed, and action refers to how a target is changed from a large screen view to a small screen view. In particular, there are 5 target categories, including data, encoding, interaction, narrative, and reference layouts. We also divide 5 action categories. Recompose actions refer to changing the existence of a target, such as removing data records and changing an encoding channel. Rescale actions change a target from a bigger state to a smaller state or vice versa. For example, reducing width is a common rescale action. Transpose actions transform the orientation of targets, such as transposing the x and y axis of a chart and serializing the layout of elements that are originally arranged in a horizontal direction. Reposition actions refer to altering the position of targets, for instance, externalizing annotations to the outside of a chart or relocating annotations to different positions are example reposition actions. Lastly, compensate actions include techniques used to compensate for the loss of information. When removing labels, authors can add a toggling option for whether to show the removed labels. Demonstrating targets and actions on one of the previous examples, remove encoding pattern has encoding as target and remove as action. Similarly, disable hover interactions pattern is decomposed by interaction feature target and remove action. Lastly, serialized label marks pattern is categorized into the combination of layout target and serialized action. Overall, rescale and remove actions were most commonly used, and data and encoding targets were less frequent. Sometimes authors make bigger changes like adding an encoding channel. We suspect that the automatability of these frequent strategies plays a role in their popularity. That is, authors may try to avoid substantive changes which are more effortful. Although it's not very frequent, the fact that authors are exploring more complex transformation techniques implies that other strategies than simple transformations can sometimes be preferable. We also notice that not every combination of target and action is feasible. For example, most reposition actions are defined on the physical position or arrangement of elements, and data targets do not have such physical attributes. So the combination of data targets and reposition actions are not likely to be possible. However, repositioning interaction features is less explored except fixing the position of interaction feedback. Also, While removing interaction feature is quite common, how to compensate such changes may need a more research attention under responsive visualization context. Several observations from our design pattern analysis suggest that responsive visualization design is characterized by a set of trade-offs. We often observed different sets of authors using different strategies for those with similar representations, as we saw in the example cases. This suggests that there may not be a single best solution. In addition, some authors introduced new revisions to a small screen view to compensate loss of information, like using toggles and numberings. This implies that design strategies for one problem may result in other problems. As a formative work, we also did a survey of 19 visualization authors about their practices and principles for responsive visualization. On average, they had about 4.8 years of experience in designing responsive visualizations. Our survey indicated that authors may think it's very important to maintain the message of their visualization while adjusting information density for smaller screen devices. Given several design guidelines, such as maintaining aspect ratio or acknowledging interaction difficulty on mobile devices, authors ranked maintaining main messages or takeaways as the top most important principle guiding their decisions. Thus, we characterized responsive visualization design as a trade-off between information density and preserving a visualization's intended messages. We observed that many examples apply strategies either about reducing density or about retaining messages or takeaways. For instance, given a line or area graph with a landscape aspect ratio, some authors remove records to adjust graphical density, and others reduce the width of the chart to maintain data points. We identify three forms of density challenges. First, graphical density refers to difficulties like when maintaining a large number of objects in small screen views results in a higher information density. Interaction complexity challenges happen when an interaction feature is no longer visible on small screen because immediate rendering and/or precise manipulation is limited. Layout can be challenging when it is difficult to keep the arrangement of bigger objects like individual visualizations or interaction widgets. Responsive transformation strategies may also result in different types of message loss, and we identify 5 forms of such message loss. Given a large screen view, if an author omits several data points or annotations to handle graphical density, it results in loss of information. Removing interaction feature due to interaction complexity causes loss of interaction. Authors often compensate loss of information using toggle interaction, but it may reduce the discoverability of those toggles and tabs. Next, due to the smaller screen size, serialized elements or transposed views might not be visible within a single scroll height, which makes it hard to compare objects across visualizations. Changes in graphical perception can result from responsive transformations like disproportional rescaling, changing bin size, etc. In particular, graphical perception between different versions of responsive visualization can change for various reasons. For example, disproportional rescaling, like reducing width, can make a slope steeper. Increasing bin size can hide some distributional details. Transposing axes often results in different shape of distributions between responsive views. Lastly, if an author serializes labels and marks, the ratio of X and Y positions changes due to the increased offset between the marks. Avoiding loss of messages or takeaways is difficult because authors have to carefully consider changes in visual attributes. Prior insight-based visualization recommendations estimated insights using statistics measured on data values, such as linear regression coefficients, to estimate a trend message. However, statistics on data values are often not useful because responsive design transformation uses the same data, and those statistics seldom change between responsive views unless an author filters out some of the data, like removing records. In addition, removing some part of information may strengthen a message if the omitted information was not critical. Therefore, to handle density message trade-offs, authors need to think carefully about what they want to keep conveying in small screen views. for example, through ranking different messages. Design iterations for exploring a large design space are often tedious, coupled with the complexity of considering density-message trade-offs. These challenges motivate an automated approach toward responsive visualization design recommendation that helps authors explore various possible transformation candidates more efficiently. To motivate future work for automated responsive visualization design recommendation, we first proposed formulating responsive design recommendation as a search problem from a source large screen view to a target small screen view. To enable this, future work should encode responsive design strategies in a formal way. This could include defining minimum size of visual marks to be perceived or conditions to which responsive strategies are applicable. Declarative grammars will be useful for a recommender to populate a wide search space given a large screen view. Furthermore, to address dense message trade-offs, we need to evaluate message preservation between large and small screen views. Considering that prior insight-based recommender approaches tried to estimate insights from analytic tasks on visualization, such as difference trend or correlation, a future work might quantify message preservation by estimating analytic insights using visual attributes instead of data values, as they are invariant across design changes. In summary, we characterized 76 design patterns for responsive visualization by comparing 378 pairs of responsive visualization design cases. Various targets such as data, encoding, layout, interaction, etc. are explored for responsive design transformation through different actions such as adding, rescaling, externalizing, toggling, etc. We further identified different density challenges and forms of message loss comprising density message trade-offs in responsive visualization. This informs us that relationship between responsive design techniques and their downstream effects is not always straightforward, making it hard to find a single best solution. Thus, we suggest future work for an automated approach to responsive visualization design recommendation by outlining interesting research directions. This is the end of my talk about design patterns and trade-offs in responsive visualization for communication. Thank you for listening to this talk.
Thank you, Hyeok, for the great work and the interesting presentation. We now open the floor to question and discussion, and we already have a few questions already from the audience. So the first question we have is from Jason Dykes, who asks, to what extent are guidelines dependent on aspect ratio as well as size of screen? It seems to assume the iPhone is portrait.
Yeah, that's really interesting question. So we mostly looked at portrait aspect ratio on iPhone screen for small screen views, because when we looked at how those responsive visualizations are produced, many authors are condition their views by the width of the screen. So it's like not the matter of how the aspect ratio is. It's like, so like regardless of portrait aspect ratio and landscape aspect ratio, the width of the screen size is mostly the determinant when conditioning responsive views. So we actually didn't look at changes specific to aspect ratios, but that's really a great point that we can look at in the future.
Okay, thank you. So now let us go to the second question. So it's from Andrew McNutt. So it seems like you partition designs into large format and small formats. Do any visualization fall in between, maybe in a desktop or tablet or phone partitioning? If so, do those exhibit any notable differences?
So we didn't explicitly look at like tablet screens, etc. But I think the prior work from Jane Hopswell might provide some intuition about that. And also, in general, many changes are gradual. So if you apply a set of transformations on tablet view, and then you add more transformations for small screen view. So it's more like a gradual steps. So that might answer your question.
Okay, thank you very much. Let's do a couple more questions. So our third question of the day is from Wolfgang Ackner. So the question is, do design guidelines for mobile operating system also include recommendations specific to visualization? In brackets, he says, in my honest opinion, many are not really applicable within visualization.
Oh, yes, that's also a really interesting question for future work. So what we did is most likely finding out generic constraints for each design patterns, which is also available in online gallery. But like to make it much more effective for actual recommender, we should look at specific constraints for actual cases, and that's actually a part of what I'm currently doing for now. Mm-hmm. Yeah.
Okay. So let's go to our next question. This is from Gabriela Molina. It sounds like going from a large screen to a small screen mainly leads to multiple types of loss. Did you find any cases where the small screen fits better than the large screen for specific visualization or message?
So when we define types of laws, it means like how the message or insights from between large screen view and small screen view changes. So we actually didn't look at what is better. So we just assume that author try their best for delivering their messages. But one kind of interesting thing was that when some interactions like requiring direct manipulation, such as like hypothesizing their answers on a actual graph, something like that, is really good on small screen views. But yeah,
Okay, so let's go to the last question. This is from Stefan Bruckner. So very interesting work, thank you. Did you also consider the effect on interaction mechanism and modalities?
So yeah, that's also a really interesting question. All the questions are so interesting. Thank you. For interaction mechanism, sometimes we could observe like authors trying to add some like automated interactions. Like when there's a map visualization, authors can simply add a GPS feature so that people can easily locate their position or their location on the map. But like that kind of interactions were good for small screen views, and then on the large screen view, it lets people search different regions one by one, because like you can engage better with complex interactions on desktop. So that kind of thing is what we observed. But yeah, we should also think about how interaction modality can think about how interaction modality affect responsive transformation strategies. Yeah.
Okay, so obviously we have further more questions and we don't have time to actually answer all the questions live here. I would encourage us to go to Discord to actually have further more discussion on this paper and on this topic. So I would say thank you everyone for the fun and interesting discussion. Let's thank our speaker again for the great work and the interesting talk.
Thank you, everyone.
Hello again. Now, let us move to the second presentation in this session. Our second paper is on ClusterSet, optimizing planar cluster in categorical point data. It is a joint work by Jakob Geiger, Sabine Cornelsen, Jan-Henrik Haunert, Philipp Kindermann, Tamara Mchedlidze, Martin Nöllenburg, Yoshio Okamoto, and Alexander Wolff. Presenting the paper is Philipp Kindermann, and now I'm going to hand over the stage to Philipp.
Hi, I'm Philipp Kindermann, and this is my EuroVis talk about cluster sets. This was joint work with Jakob Geiger, Sabine Cornelsen, Jan-Henrik Haunert, Tamara Mchedlidze, Martin Nöllenburg, Yoshio Okamoto, and Alexander Wolff. In this talk, we want to explore different ways to visualize categorical point data such that close points are clustered. Imagine you have a map, for example, of Manhattan here, and there are a bunch of points of interest that you want to visualize. For example, you're interested in subway stations, in hotels, and in hospitals. This gives us different sets of points, and these sets we want to visualize while keeping the spatial locations. There are already a few algorithms that do that. For example, bubble sets, where every set looks like soap bubbles, or line sets, where we have a simple line through all the points of the same category. Then there is kelp fusion, where we represent the sets by trees, but if we have empty regions, then we might use a polygon here. And map sets, where the whole map is split into colored regions that may only contain points of the corresponding color. In all of these approaches, the points of the same category are always completely connected. In this talk, we want to relax this connectivity requirement to preserve the locality of clusters. And that might give us a visualization like this one, where we don't have a single green region but 2 green regions, 4 blue regions, and 3 red regions. The design goals of our approach are the following. We want the categories to be represented by distinct colors. We want to form clusters which are subsets of points from the same category. And these clusters should form distinct regions in the plane. For these clusters, we want that the points inside a cluster are sufficiently close, and we want to have a small number of clusters per category. The question is, what do we mean with sufficiently close? For example, these 2 green points are in the same cluster, but are further away from each other than these 2 red, which are not in the same cluster. However, if we have denser parts of the map, then we don't want to have the same metric that decides which points are close than if we have not so dense parts. So instead of looking at the Euclidean distance, we use a suitable proximity graph to define which points are close. We propose the following pipeline for an algorithm. First, we want to pick a proximity graph. There are several established algorithms that can do that. For example, the Delaunay triangulation. In a Delaunay triangulation, we have a triangle between 3 points if and only if the circle through these 3 points contains no other point in its interior. In the Gabriel graph, we have an edge between 2 vertices if the circle that has the connection between them as a diagonal does not contain any other point. So we also have this edge here, but not this up here. And a beta skeleton is a generalization of this. Here we don't use circles, but we can narrow them or make them wider. And this might give us even a non-planar graph. If we choose beta to 1, then these objects are exactly circles, so we get the Gabriel graph. If we set beta to 0, then they are just segments, and we get the complete graph. In the second step, when we have the proximity graph, we want to find a planar spanning forest in it. So for this example, if these points are red and these are green, then this would be a planar spanning forest. In the third step, we want to augment this spanning forest. So between vertices that are in the same component, we can add more edges to make it a bit more dense. And finally, after we've done that, we want to render our solution. For that, there are again different approaches. For example, we can use the line Voronoi diagram, which is what we used in this example here. Or we can simply display a planar spanning forest that we computed in step 2, like here. Or a third approach is to take what we have after step 3 and try to draw empty polygons around these edges. Let's have a look at a smaller example. we have 3 sets of points here. First, we create a proximity graph with a beta skeleton with low beta, and then we can already remove all these edges that are not monochromatic because we don't need them anymore. Now we find a planar spanning forest, and in step 3 add back all the edges we can inside the same cluster. And now we use the polygon representation to render the solution. Algorithmically, the most interesting step is step 2. So we now want to focus on this step. We developed 2 heuristic algorithms. In both of them, we want to pick edges from our graph and move it to a second graph G', such that in G' in the end we have a planar spanning forest. And in all algorithms we remove all the bichromatic edges from the input here. In the greedy algorithm we do 3 steps. First, we remove all edges from G that are in the same component here. In the beginning, that's nothing. Then, we take an edge here that is crossed by a minimum number of edges. So, for example, this planar edge here, and move it over there. And then we remove all edges from G that used to cross this. So, as long as we have planar edges here, we don't have to do step 3. But now these 2 vertices are in the same component here, so we have to remove this edge. We can keep planar edges, move them over, repeat steps 1 and 2, and by step 1 it might even happen that another edge becomes planar that we can also move. At some point there will be no planar edges left, so we have to pick one that has minimum number of crossings. For example, this one here, move it to G', and now remove this edge that used to cross it. In the final step we have to pick another edge between the red ones, because they are only crossed twice, while the blue edges are crossed 3 times, move it to G', remove the remaining edges, and we're done. The second heuristic is the so-called reverse greedy. In the beginning, these 2 algorithms do exactly the same. We remove edges between the same component, and we move all non-crossed edges to G'. So let's do that. But at some point, when we only have crossed edges here, instead of picking the edge with the fewest number of crossings, we remove the edge with the largest number of crossings. For example, this one here. Now we again have planar edges that we can move. We have to find the edge with the largest number of crossings, remove it. This has the largest number of crossings, remove it, and add planar edges to G'. And then again we get a solution. We will later evaluate that both these heuristics give us very good solutions in practice, but in theory they can be quite bad. So let's have a look at some examples. Let's say we have a blue star with k leaves, and we have a red star with k-2 leaves where the leaves are connected by a path, and we have 3 green vertices that also intersect the blue edges. What would the greedy algorithm do here? It first picks all the planar edges, and then it picks a green edge because it has the fewest number of crossings. Then it removes all the edges that crossed it, and now it might pick the other green or one of the red edges. It doesn't matter, we get the same solution, which has k+1 blue clusters, 1 green and 1 red. On the other hand, the reverse greedy performs very well here. It again picks this path, but now it successively removes all the red edges because they have the largest number of crossings. Then it removes the green edges, and finally it can pick all the blue edges, which gives us 1 cluster for blue, 3 for green, and only 2 for red. On the other hand, if we slightly adjust this example and move this path from here to here, then it's the other way around. Now the greedy first picks the planar edges, then it picks a green edge, then it picks another green edge, and it can pick all of the red edges. And we get in total 3 clusters. The reverse greedy, on the other hand, it first picks the planar edges, and then it starts removing those red edges. Then it removes 1 green edge and can pick 1 blue for it. And finally it can pick the other green edge. So now we have 1 blue cluster, 2 green, but k-1 red. So there are examples where greedy is arbitrarily worse than reverse greedy, and examples where reverse greedy is arbitrarily worse than greedy. So for this problem, we developed the greedy and the reverse greedy heuristic, and then we also developed an ILP formulation that can solve it exactly, but is quite slow. In general, this problem is NP-hard even when all the points are in the same category, which was proven by Janssen and Böginger in 1993. Let's go back to our pipeline. We now want to have a closer look at the first step, proximity graphs. We have these three different ways to create a proximity graph. And actually the Gable graph is a subgraph of the Delaunay triangulation. Now the Delaunay triangulation is known to be planar. Now the whole second step, finding a planar spanning forest, is trivial as long as the graph is planar. So these don't give us very interesting future steps. Now as long as the graph is planar, the monochromatic edges in the proximity graph already give us clusters that cannot be extended. So it doesn't make sense to compare our heuristics on planar graphs. Instead we focused on beta skeletons. And now I briefly want to show you an example on the influence that beta has on the solution. Here we can see, for beta equals 0 we get a very small number of clusters, but we also have connection between vertices that are not really close. While for beta equals 1 we get many clusters and most of the points are singletons, which comes from the fact that this is the Gabriel graph which is planar. Instead, choosing something in the middle seems to be the better choice. We conducted a case study for our algorithm on 3 datasets, all of which you have already seen in this talk. The first set contains 78 points that represent the facilities of University of Bonn, where the categories are the departments. This is the data you saw on the title slide. And the left example was a simple Voronoi diagram that we used for those colored points, while the right example used our greedy algorithm on a 0.5 skeleton and shows both the line Voronoi diagram and the polygon representation. And here we can see, although most of the yellow and brown facilities are close to the main campus, they are still split into different regions, while in our approach they form one contiguous one. Also, these 2 purple points, although they are close with nothing in between, are in different regions, while our approach puts them together into the same one. The second dataset is from Manhattan and has been used as benchmarks before. That's the one that you saw on the first slides. Here, if we compare the different styles from the literature, we can see that the bubble sets, line sets and kelp fusion have many crossings between their sets. They might be at very small angles and they might even be very close to other facilities. While in the map sets we don't have crossings, but those polygonal shapes can be very complex. For our representations, the tree representation is quite similar to the kelp fusion and line sets and also the bubble sets, where we don't really see the clusters very well since everything is just connected by lines. However, in the polygon and in the line Voronoi representation, we can clearly make out the clusters. And in this example, the line Voronoi representation seems to work particularly well, because the points are almost evenly separated throughout the map. On the other hand, in other maps where we might have large empty regions like here, the polygon representation seems to work better. The third dataset we extracted from OpenStreetMap, and it has 16,320 points and 123 different categories. This is almost the same spatial extent as the first dataset from University of Bonn, but of course it has many more points of interest. A smaller part of this dataset we already saw here, and now we want to experimentally look at the number of clusters we get depending on beta, where green is the optimum solution, red is the greedy, and blue is the reverse greedy algorithm. We can see that the greedy is slightly better than reverse greedy, but both are very similar to the ILP solution. Also, we can see that in the beginning we have some drastic changes, and in the end we have some even more drastic changes, while in the middle around 0.4 to 0.7 not really much changes. And since the number of clusters don't seem to change too much somewhere in the middle here, this seems to be a good trade-off between our design goals that we want few clusters but vertices still to be close within the cluster. Based on this dataset, we also conducted quantitative experiments on the running time and the quality of our solutions. To create smaller data from this large dataset, we took the region that the data lies in and split it into 9 squares. For each square, we took the center point, and for different ends from 50 to 250, we found the closest points to these centers. This gives us 9 times 5, so 45 different datasets. And for each dataset, we ran experiments for beta equals 0.5 to 0.9 in steps of 0.05. You can also download the code we used for these experiments from GitHub. First, we want to briefly talk about the running time. For all of these instances, both the greedy and the reverse greedy algorithm always could find solutions in less than 50 milliseconds. The ILP worked well for instances of 50 points where we got solutions within 11 seconds, but even for 100 points it required up to 1.8 hours, and for 150 points there were some instances where we stopped the solver after 2 days. So we only have optimal solution for some of the instances with 150 points and for none of those with 200 and 250. I will now briefly show the results for beta equals 0.5. You can find the others in the supplementary material. We use whiskers plots where the middle edge is the median and the top and bottom boundary of the rectangles are the 75 and 25 percentiles. We can see here that for small examples where both heuristics perform very close to the ILP, and while for larger number of points it gets a bit further away, the difference between the median is still at most 5 clusters here. Also, both heuristics seem to perform equally well. This is also the case for those instances the ILP could not solve and for larger instances. In fact, of all the instances we had here, only 66 times the greedy heuristic was better, 126 times the reverse greedy algorithm was better, and 213 times they got the same number of clusters. And as further evidence that our algorithms perform very close to the optimum, we are also plotted for every beta and the instances the ILP could solve, how many more clusters our heuristics needed in the worst case. And we can see here that only few data points have more than 10% more clusters than the optimum. Let's conclude. We developed the pipeline for the ClusterSets method. We developed heuristics to solve step 2, and we mostly focused on beta skeletons in step 1. For step 4, we considered 3 different options, where we prefer the line Voronoi and the polygon representation. We did not yet talk about step 3. Here so far we only add edges back in arbitrary order without creating crossings. But one could further investigate if there are better algorithms here. Also, all our points have one single category, and it would be interesting if these algorithms can be adjusted when we have more than one category per point. Thank you for watching.
Thank you, Philipp, for the great work and the great presentation. Now we open the floor to the questions from the audience. So type in your question in the chat, either in YouTube or in Discord. So we have our first question. It's from Andrew McNutt. So the question says, when you say that ILP is quite slow, is it so slow that it doesn't run on a common number of points for this type of problem, such as 78 or 96 points in your case study, or are you more concerned with asymptotic performance?
Yeah, thank you for the question. So for the case studies, we could get solutions within 15 to 20 minutes, but it's still reasonable let's say up to 75 points or something, and after that it can become more than an hour. And like I said, we had some examples with 150 points where after 2 days we had to stop And we don't know how many more days it would have taken to get a good solution. So as long as you have fewer than 100 points, you might use it. But if you have a large map, then I would not try, probably.
Okay. So now let us go to our second question. It's from Max Sondak. The question is, how does the greedy algorithm planar spanning forest compare to the ILP on the examples you have? Is it getting close to the optimal or far off? And is there any bounds or how far of it can it be?
So in the examples in the case study, it was often not by more than 11%. So the solutions we got from the greedy and the reverse greedy, they were still very close to the optimum. And also when we broke down the examples into smaller cases where we don't have that many points, it was always very close. And on average, I think it was 4 or 5% off from the optimum. But of course, there are examples where you can be terribly bad. In the beginning, I showed you the examples of greedy and reverse greedy that are quite constructed, but there you can be off by any factor. So instead of having 4 clusters, you can have any number. So in the worst case, it's pretty terrible, but it seems that in practice, it does seem to work quite well and you get quite good solutions.
Okay, thank you. So we have our third question is from Jason Dykes. So the question is, relative size of each color seems quite salient, important and sensitive to external points, but there's scope to vary this at the edges, places where you have very few points. Then the question is, can you tweak things to get overall area sizes proportional to the numbers of items in each class?
It seems to be quite tough because, one part of the design principle was that if you have a map where you have a lot of dense stuff and then you have a lot of sparse stuff, then you still want clusters here with few points. And then, of course, by design, you will have a small cluster that will have a large area. If you don't want that, then, of course, you can pick a proximity graph by just saying, okay, we have an edge between all vertices that have some maximum distance. And then probably you will get some kind of that effect. And on the other hand, of course, you can do different stuff in the rendering step. Maybe there's a smarter way to do this than just use line Voronoi or polygon visualization. And then maybe you can get your goal. But at the moment, I don't know how to do it.
Okay. So let me ask the last question for you. I have a last question. So in your approach, you only consider data in which every point belongs to exactly one category. But in practice, you could have some points that belong to more than one category. So do you have future plans, or what are your plans to expand your approach to cover this specific case?
So we are planning to also look at that case. That's we started with that problem and then quickly found out it's pretty tough. So let's only look at single color, and then we got some good solutions. And the next step, of course, is to also have a look at that. The problem is that you can have some pretty degenerated stuff in the proximity graph. You can have edges that have different colors, and then it's not clear if they're allowed to cross or not, depending on which cluster you put them in. And then it gets even hard to define the problem in a way that makes a lot of sense. So we have to be a bit more careful. What is allowed? Where can you have crossings? Where can you not have crossings? How do these clusters look like when they have points of different color, or a point with 5 different colors? Is it in 5 clusters? Do you have them with overlap? So there are many questions that we have to ask ourselves first. How do we want to design this?
Yeah. So just a note, if anyone is interested, the code and the implementation is available on GitHub, and you could find it on the paper. So thank you everyone for the exciting discussion. Let's thank our speaker again. And I would suggest that we continue further our discussion on Discord. So let's thank our speaker again. Thank you very much.
Thank you, Alfie.
Hello, everyone. Now, let us move to our final paper for this session. Our final paper is on optimal axis for data value estimation in star coordinates and radial axis plots. It is a joint work by Manuel, Rubio-Sánchez, Dirk, Joachim, Lehmann, Alberto, Sanchez, and Jose Luis Rojo-Álvarez. Presenting the paper is Manuel, and I'm going to hand over the stage to Manuel.
Hello, my name is Manuel Rubio-Sánchez. I'm a professor at Universidad Rey Juan Carlos in Madrid, Spain, and I'm going to present our work on optimal axis for data value estimation in star coordinates and radial axis plots. So radial axis plots are projection methods that map high-dimensional data onto a lower dimensional space, which is normally a plane. So data samples are represented by points or dots, and it is also possible to include information about variables by showing a set of axis vectors where each one is associated with a variable. It is also possible to include axis lines that allow users to estimate original data values by projecting points orthogonally onto these axes. So for example, in the image on the right, we have a data set of cars, and we can estimate the value of horsepower for the car represented by the red dot by projecting it onto the axis. So in this case, we would guess, or we would estimate that the value of horsepower for that car is about 150. So the whole paper revolves around this idea of estimating data values optimally. And we're going to show how to label the axis optimally, how to choose alternative axes that allow users to estimate values more accurately. We're also going to provide guidelines for choosing axis vectors and therefore visualizations, whether we would like to update an axis vector or add new axis vectors into the plot. Now the paper is very specific. It's mainly intended for experts in radial axis methods, and it's halfway between a theory paper and a technique paper. So we also provide several theoretical results, and all the proofs and derivations are in the supplemental material. Before we begin, let's take a look at the several radial axis methods that we analyze in the paper. The first one is star coordinates, which creates a linear mapping from your n-dimensional data space onto the plane. The axis vectors are simply the components of the transformation matrix, and the points are linear combinations of the axis vectors, where the coefficients of the linear combinations are the attribute values of the data samples. In star coordinates, the vectors indicate directions in which variables increase. And I've written this in quotes because we're going to see that in fact there are better directions. The length of the axis vectors indicates the importance of a variable. And it's important to note that this is an interactive technique. So users can select the axis vectors interactively in order to accomplish certain tasks. For example, in the image on the right, we've selected the vectors in order to plot data with high values of horsepower and acceleration, but low values of miles per gallon at the top of the graph. Lastly, in the bottom, you have the notation that we're going to use throughout the slides. Orthographic star coordinates is a variant of star coordinates where the transformation matrix is orthogonal. In the context of this paper, it's important because if you add axis lines to orthographic star coordinates, the estimates are going to be more accurate than if you just add lines to star coordinates. Also, it's important to note that we're going to consider that we obtain a particular configuration of vectors for OSC by orthogonalizing some other configuration of axis vectors in SC. So this implies that the columns of V and V orthogonal are going to span the same subspace. Principal component biplots are generalizations of the well-known PCA plot. In biplots, the estimates are dot products between the points and the axis vectors. And these points and axis vectors are obtained by minimizing that optimization problem, where the goal consists of reducing the discrepancy between the estimates and a centered version of your data. Now, because the problem finds the points and the vectors simultaneously, it's going to provide the best possible plot regarding estimation accuracy. So it's going to provide a lower bound for the total estimation error across an entire data set. Adaptable radial axis is a hybrid approach between star coordinates and principal component biplots. In this case, users can select arbitrary axis vectors, so it's an interactive technique, and the points are plotted in order to maximize the estimation accuracy for a fixed set of axis vectors. The optimization problem in this case is identical to the one for biplots, but only the points are the variables. So here you have the solution, and it's worth mentioning that the estimates for this technique are identical to the estimates for OSC. So having seen the diverse radial axis methods, the first section of the paper introduces how to optimally label the axis, or in other words, how to optimally calibrate the axis. Now this sounds obvious, that you would have to perform this operation, but you have to be careful because you can't just apply the calibration approach in biplots to your method, because it might give you very incorrect estimates. So for example, in this case, we've used a data set of cars, and the values for displacement, the displacement variable are between 68 and 455. So if you notice on the image on the left, if we project the points orthogonally onto the axis, most of the values are going to be less than 68, which would be false. So ideally, we would like these points to lie within the gray region. And if you scale the axis and shift it appropriately, well, we see that the labels appear in other locations, and now most of the points lie within the gray region. So you can use line axis within any dimensionality reduction method, but you have to be aware that you have to label the axis correctly. We accomplish this by solving that optimization problem. The alphas would be the scalings of the axis, the betas would be the shifts, those dot products would be the estimates, and finally x would be the data values. So these are the optimal solutions. They are pretty straightforward, but you can find the full derivations in the supplemental material. And finally, the final formula indicates where you would have to place a particular label. Even though the previous calibration approach enhances the estimates considerably, it's possible to find different directions, different axes, that lead to even an increased accuracy when estimating data values. So for example, in the image in the left, we can assume that the values for displacement increase from left to right. But actually, a better direction is this oblique new direction in the right at about negative 20 degrees. So we propose using these new alternative axes, and we've analyzed them in great depth in the paper. This is the optimization problem. Again, we have the estimates, shift parameter, and the data. And in this case, we don't need a scaling parameter because it's already embedded in V, since V is the variable of the problem. So these are the solutions, and again, you can find the details in the supplemental material. It's interesting to analyze the angle differences between the original and optimized vectors. In general, these differences will be small, as we can see in the example, and also from these distributions that we've obtained through a couple of simulations that we've done. And the angle differences are usually less than 60 degrees, but some can be larger. And in these cases, this is a clear indication that the original choice of axis vector is probably poor. So users should really think about the original axis vector and consider updating it maybe to a direction that is more similar to the optimized vector. In general, we would like the optimized vectors to be as similar as possible to the vectors that we're using in our radial axis method. And we've seen that the optimized vectors are similar to the ARA vectors, but not to the star coordinates vectors. In fact, there seems to be an inverse relationship between the lengths of the star coordinates vectors and the lengths of the optimized vectors. But there should be some middle ground. So we also propose to scale the axis vectors of star coordinates so that they will be as similar as possible in a least square sense to the optimized vectors. And this scaling parameter can be found by solving this optimization problem. And well, the solution is expressed in this nice closed form formula. And again, the details are in the supplemental material. We have also analyzed the information provided by the lengths of the optimized axis vectors. So initially, we thought that the larger vectors would indicate better estimates because this is exactly what happens in ARA plots. So as you stretch a vector in ARA, the labels get squashed together, and this means that the method is going to focus on representing those points or represent the values for the variable better. So we assume that this would happen also when using these optimized vectors, and in fact our initial results seem to suggest that, but we were using standardized data where the variables have the same variance. And it turns out that this only happens if the variables share the same variance. If not, then the lengths of the optimized axis vectors are more correlated with the variance of the variables. So this is clearly an unexpected result worth mentioning. In this slide, we show a comparison of estimation error for the three methods. And when we apply the calibration approach, well, the estimates are enhanced, obviously. And, well, you have the same accuracy for ARA as for OSC. And the estimates for star coordinates are not as good because, well, as expected, because the estimates for SC are poorer than for ARA and OSC in the first place. So this was expected, but what was not expected is that if you apply the optimal axis, then the accuracy for the three methods is the same. So this is pretty curious. Note that the points and axis vectors in all the three cases are different. And also, what this indicates is that it doesn't matter which method you use as your starting point. You might as well just use plain star coordinates, and then if you apply the optimized axis, you're going to achieve the same accuracy as if you had started with ARA or OSC. So now we're going to see how we can incorporate the optimized vectors in other methods, and in particular in RadVis. Here we've calculated the vectors and located them at the anchor points of a RadVis plot. The dataset is the olives dataset that is well known. And what we can see is that the vectors ideally should point in not towards the center, but in the opposite direction, as for example this vector. Some vectors don't point exactly in that direction. And this is the most interesting vector here because it points inwards. And this is very strange because the values of a variable should increase in the direction of the anchor points, but they seem to increase in the opposite direction. So this clearly indicates that the ordering of the variables here in the Radvis plot is poor. The palmitoleic variable should be probably placed somewhere around this zone. So we've done that, and we've swapped the palmitoleic variable with the palmitic one, and now we have a better ordering of the variables around the Radvis circle. And nevertheless, you can consider these directions when, for example, trying to see which values, which points have the greater values for a particular variable. Now, if we didn't color the points in any way, we would assume that the points with larger palmitoleic values are these ones over here, because these are the points that are closest to the anchor. But in fact, that's not the case. And now if we visualize the vector, this red vector is the same as this one, but just scaled and located here in the center. Well, we see that, in fact, the variables increase in this diagonal direction. So, in fact, now we can see that, in fact, we could have the greater values either in this zone or in this zone, and in this case, they are in this region. A drawback of the previous optimal axes is that they lead to inconsistent models. They are inconsistent because the projected points are the same, but we're using different vectors. So now our new goal is going to be to update or add one axis vector while the main remain fixed, and we want to maximize the estimation accuracy, but with a plot that is consistent with the model, with the star coordinates or ARA. So in the first approach, the user is going to define an orientation, and subsequently the method is going to find an optimal direction and an optimal length for the vector. In this case, we're adding a new variable into the visualization. Naturally, a user could select multiple orientations. So we propose drawing a colored curve on the plot to indicate the optimal length of a vector in any orientation. In this case, the color corresponds to the estimation error, and we can see that the best values are obtained here in the fourth quadrant. This is the optimization problem that we'd have to solve. V sub n is the new vector in a particular direction. Lambda is just a scalar that can be positive or negative. And the solution for star coordinates is the minimum of a fourth degree polynomial. So you basically have to compute the roots of a cubic polynomial, which can be done without any problem. And for ARA, the objective function is a quotient of polynomials, so the function is much more complex, and we use a direct search method to find the solution. The optimal vector that leads to a consistent model over any orientation can be obtained by solving this optimization problem. In this case, v sub n is the variable. And for star coordinates, we use a gradient descent method, while for ARA, the function is more complex, and we use a recursive search approach. So to recap, we've shown how to label axes optimally, that is, how to calibrate them. We've also proposed using alternative axes for enhanced data value estimation. We've proposed a strategy for updating or adding vectors that leads to consistent models. We've provided guidelines for choosing axis vectors, and in particular for identifying poor initial directions. And we've also mentioned several theoretical results, and you can find the proofs and derivations in the supplemental material. Thank you very much for your attention.
Thank you, Manuel, for the great presentation and the great work. Now we open the floor to questions from the audience. So I remind people to type your question in the chat, either in the YouTube or in Discord. So while we're waiting for questions to come in, so let me start with the first question. The optimal axes can also be included in other plots, and they can be used within EuroVis to assess the quality of available ordering. I was wondering if there are any plans to do a comparison of these approaches using different criteria to define the quality of an arrangement.
Okay, yeah, sure. In fact, when we select, for example, a new axis vector, we are considering this in the entire paper. We are considering the estimation error. But for example, you can consider other criteria. For example, you might want to locate a vector such that the cosine between the rest of the vectors resembles the actual correlation between the variables. Mm-hmm. So you would use correlation instead of estimation error. So you can find other types of criteria, such as that one. Yeah. So
if you could define other types of criteria, how could you also put sort of like semantic meanings to the axis and to the vectors? Would it be possible to do such a thing?
Semantic, I'm not sure. This is more of a quantitative approach. Mm-hmm. So I really haven't thought about that. It's a good question. For now, we're just centered on numerical data. So I'm not sure how to really incorporate semantic information. But again, there are other measures of, say, variable importance or variable relevance that can be taken into account, and maybe some kind of semantic interpretation, could be also exploited somehow.
Okay. So why don't I ask the last question of the day, of the session? So our final question is, I was wondering if you have any plans to explore your approach with tasks such as searching for cluster structure, detecting outliers, and separating classes. And if so, could you tell us about your possible approach?
Okay. For the moment, we haven't considered these approaches, but it's true that besides the estimation error, the correlation that we talked about, of course, now you can. I think this has not been explored, and it's how to select the axis vectors to visualize clusters or separate classes. I mean, there are, of course, methods in the literature, very well known, like linear discriminant analysis or whatever, methods that will separate your classes and so forth. But I'm not sure that we've explored, how to locate a new vector, in order to, maybe visualize or separate classes even better, in a gradual approach. So, doing what a user would do in practice, mm-hmm. instead of just relying on an automatic algorithm, incorporate some interaction approach, but aided by these other algorithms, to give you some quality metric that you can follow.
Okay. So I like to thank everyone for coming to this session and the exciting discussion. So let's continue our discussion in Discord and Topia. So let's thank our speaker again. And before closing this session, I'd like to thank all of our speakers today, all three of our speakers, our technical supports, and our student volunteers. Let's give a big round of applause to everyone and hope to see everyone in the next session. So thank you, everyone.